In this lesson, we'll look at various transformations of graphs. Here are placed a few pictures from real life or art pictures that represents transformations. For example, a reflection, a translation. This is also an example of translations, as well as Möbius strip. On this picture, we can observe a lot of symmetries. So line symmetries, central symmetries, rotations, and also translations. These two pieces of art shows us some dilations, and another Escher work you can observe various translations or rotations as well. When we graph various functions, it's useful to know the basic shape of the function. For example, in this case, the basic shape of a function is absolute value, so we can know this off heart, and then create a new function by different transformations. For example, in this case, we're moving down the basic function absolute value of x by 4 units, so we're subtracting 4 from absolute value of x. Therefore, knowing how to obtain a graph of a new function from the previous function by, for example, translations is quite useful. We don't have to use table of values anymore. We can just use the knowledge of the basic function and appropriate transformations. So generally, if we have a graph of a function f of x, to create a graph of the new function, that is f of x plus certain constant number c, we translate the original graph by the vector 0, c. So we translate it vertically by exactly c units. Since we are going to use vector notation, first of all notice that I'm going to use this pointy bracket to distinguish from the point or interval. So we'll know that such bracket will represent a vector, and also what the vector AB really stands for. Well, it's a vector that moves A units horizontally and B units vertically. So to obtain a graph of f of x plus certain constant, we apply translation by the vector 0c to the graph of f of x. The action of this translation will cause that any point x, y that belongs to the function f will be moved to a point x, y plus c. So we're adding c units to the y value, and the new point belongs to the new function g. How does it work in practice? Well, let's take an example of a basic function x squared. We'll graph gently the parabola x squared. It has a vertex 0, 0. It goes 1 across and 1 up, and goes 2 across and 4 up. So this is the basic function that we need to keep in mind. So this is our f of x. And then g of x is x squared plus 2. Therefore, every important point, for example, vertex, will be moved 2 steps up. So it's here. 1, 1 will be moved 2 steps up. 2, 4 will be moved 2 steps up, and so on and so forth. Therefore, we can make the final shape somehow like this, and this is our g of x, the green shape. Another type of translation is a horizontal translation. The graph of the given function f of x will be moved horizontally if the new function has added some constant just to the x inside the function. So such function will be obtained from f of x by translating the original graph by the vector negative c0. So opposite sign to whatever you see. This is shown here on the diagram by moving the original function absolute value of x. If we want to create a function absolute value of x minus 4, observe that x equals 4 will make this value 0. So the vertex is moved from 0 to 4. Even though we subtracted 4, the graph is actually moved to the right. So the translation that we're using is by the vector opposite to the c that we see inside, and 0, negative c0. And again, the action of this translation moves the point xy into the point x minus c and y. Look at the particular example. If we start with the basic parabola x squared, which is, as before, going through these 5 main points. That's f of x. Then the new graph of x plus 2 square will have a vertex exactly when x is -2. Since -2 plus 2 is 0, that's the lowest point that we can obtain. So the vertex is moved to -2. And all other points will be moved 2 steps to the left, as we can easily calculate. For example, double check. If x is -3, then g of x, -3 plus 2 is -1 square, it becomes 1. So yes, it confirms that this point belongs to the graph. So our graph looks like parabola shifted 2 steps to the left. And you're welcome to check some other points to confirm the movement. And now we have combination of the 2 movements. We would like to graph g of x, root of x plus 3 minus 2, using the basic graph of just root of x. Well, what kind of transformations do we need to apply to the original function root of x to obtain g of x? Well, let's think about it. F of x is root x, that's our starting function. What do we have to do with it to be closer to this formula? Well, we could first subtract the 2 from outside and then add the 3 inside the root by dx. So altogether we have already g of x. Okay, what kind of transformation operates from here to there? Well, we're subtracting outside of the function, so it's a translation by the vector 0, -2. 2 steps down. And from here to there, we need to apply translation by the vector -3, 0. 3 steps to the left. So altogether, these 2 translations could be actually replaced by single translation by the vector -3, -2. And observe how can we read the coordinates of this vector. The opposite sign to whatever we see inside the function by dx, and the same sign outside of the function. Very simple. So to graph our shape, let's start with basic function root x, which we know very well how it looks like. Starts from 0, go 1, 1, and 4, 2. It's like half of sideways parabola. That's just root of x. And then we can graph the g of x function just by shifting this original function by the vector -3, -2. So starting from the origin, -3, -2 ends here. So the vertex will be moved over here, -3, -2. This point, again, -3, -2 will be moved here, and that point, -3, -2 over there. And we can volunteer a shape. So you see, by using transformations, we don't need any calculations. Another transformation that we will talk about are reflections. So for example, if we want to obtain a new function g of x from f of x just by placing a minus in front of f of x, this will cause that all the values of the original function will be reversed to the opposite sign, which really means that if, for example, this point belonged to the graph of f, then the point reflected over the x-axis with negative y coordinate will belong to the g. Therefore, we will be talking about symmetry in x-axis. Okay, so symmetry in x-axis takes a point xy and brings it to the point x, -y. For example, a point 3, 2 to a point 3, -2. Okay, let's graph particular example. Again, we'll refer to the basic parabola, which we know how to graph easily, like that. Then to obtain a graph of g of x, which is -x squared, we have to reflect this parabola in x-axis. So 0, 0 is still the same, but 1 becomes -1. Add -1, -1, add 2, -4, and here -4, and the parabola looks like this. So this is g of x, which is negative x squared, while the original one was just x squared. And we had our regular scale 1 and 1 here. Okay, and that was our root of x plus 3 minus 2. Next we'll look at reflection in y-axis caused by using minus not in front of the function but exactly by the x. So to get a new function g of x from f of x, we reflect the graph in y-axis. Therefore, the symmetry in y-axis causes that any point xy, let's choose any point xy, for example 2, 1, if we reflect it in y-axis, then such point will become negative 2, 1. So what we did, we changed the first coordinate, but we keep the second coordinate. So xy goes into negative xy. That's a symmetry in y-axis. So as before, let's take some example. This time we're going to take example x plus 2 squared, which, as you remember, that was a basic parabola moved 2 steps to the left. So the parabola looked like this, where this is negative 2 and this is 4. Now, if we want to obtain a graph negative x plus 2, observe we're changing sign just by the x. That will be obtained by applying symmetry in y-axis to the yellow graph. So this point becomes here, that one there, this one is the same, and that one will be moved to 4. So now we connect all these points, and the parabola has a vertex 2, 0, and look like this. This is the graph of negative x plus 2 squared, while the original one was x plus 2 squared. Next exercise is to look at the combination of these two symmetries. So the outside minus indicates symmetry in the x-axis, and the inside minus represents symmetry in y-axis. And in this case, it actually doesn't matter which symmetry we apply first. So we can observe the symmetry in x-axis first, starting with this given function f of x. If we apply symmetry in x-axis, this point goes here. The 0, 0 point is the same, and this is a constant piece, and this is a straight segment. And we can pick one more point, for example, this one, it will be reflected exactly here. So connect the two vertices. So we have negative f of x. We need to move it one more time by applying sy, symmetry in y-axis. So this point is still at the same place, but that point goes here, symmetrically the same many units. And this straight piece, it will be flipped over there. Now let's connect the vertices that we have. This point will become here. So the green graph represents our final function g of x, which is negative f of negative x. And the next exercise asks us to list transformations needed to obtain the graph of 2 minus absolute value of 1 minus x from the graph of the basic absolute value function. Then after we realize what kind of transformations do we need, we're going to graph g of x. Well, therefore, let's start with the absolute value of x first. Then, to be closer to this formula, what do we need to do is add the 1. So, it's not the same yet, but let's add the 1 first. We know how to do this. This will be translation. It's a horizontal translation to the opposite sides by negative 1. So we translate by the vector negative 1, 0. Okay, but we want to have 1 minus x. So now from here to obtain negative x plus 1, we use this function as a function of x, and we're changing its sign by the x. So it will be symmetry in y-axis. Now from here, to get closer to g, we should put minus in front of the function. This can be done by symmetry in x-axis. And finally, we need to add the 2. So 2 minus absolute value of negative x plus 1. In order to obtain this final stage g of x, we need to apply translation by the vector 0, 2. We're adding 2 to the previous function. So here we have a list of transformations, and quite often the order of transformations is important. So when we graph, remember to transform the graph in this particular order. So let's start with the basic shape absolute value of x, which is a V shape like this. We have 2 diagonals with a vertex 0, 0. So we'll use yellow for this function. Now, after the translation, let's use red color to indicate absolute value of x plus 1. We're translating the yellow graph one step to the left, so the vertex will be here and everything translated one step to the left. The next step, let's use green. So here we need to apply symmetry in y-axis, so the red shape will be flipped symmetrically in y-axis, meaning the vertex becomes at 1, and the shape looks like this. In the following step, we're flipping the green shape over the x-axis to obtain a blue shape. So flipping over the x-axis, we reflected these 2 diagonals like that. Finally, our shape of g function will be in purple, and we need to apply translation by 2 steps up to the blue shape. So the vertex goes here, and your diagonal lines will go like this. This will be the final shape of the graph g of x. And the yellow one was f of x. So if we want to very clearly see the transformations again, we can name those functions. Original one is f of x, so let's stick with the same name. But the next one, after translation by 1 unit to the left, we obtain a new function. Let's call this new function f1 of x. And this f1 of x is actually the same as f of x plus 1. Now, to obtain the green function, we referred to the f1 already, and we used the minus by the x. So let's call the green function f2 of x, and this function was obtained by placing negative by the x of the f1 function. Now the next step, we used negative in front of f2, so negative f2. And this could be called f3 of x. Finally, g of x is really the same as our previous f3 function with added 2. So f3 plus 2 outside of the function. Well, we have a couple more transformations. For example, dilations. Dilations are stretching the function by multiplying it outside by a constant k. That will be a dilation, either stretching or shrinking depending how large is the number k. If absolute value of k is larger than 1, then it's a stretching. If absolute value of k is smaller than 1, then it's shrinking. So we dilate the graph vertically by the factor of k, and this transformation will be denoted by d, capital D for dilation, along the y-axis, that means vertically, and give the factor by the factor k. So the dilation affects any point xy by multiplying the y-coordinate by k. Example, again, if we start with the basic parabola, which goes somehow like this. That's our f of x. And we want to graph g of x, which is 2 times x squared, then every single point will be multiplied by 2. So instead of 1, it will be 2. Instead of 4, it will be 8, somewhere here, and symmetrically to the other side. So the graph becomes a lot steeper. It goes somehow like this. So this is g of x, which is 2x squared. That was stretching. Well, if you want some other function, for example, h of x equals 1/2 x squared, then instead of 1, the point will be 1/2. Instead of 4, the point will be 2, and symmetrically to the other side. So as you see, the graph will be wider. That's the vertical shrinking of the yellow graph. This was 1/2 x squared. And another type of dilation will be dilation in x-axis. That happens when you multiply x itself by certain constant k. Similarly as with addition and subtraction by x, that we translated the graph to opposite side, now when we multiply just x by k, the dilation will be by the factor 1 over k rather than k as before. So vertically it's the same number k, but horizontally it's a reciprocal of k. And this dilation will be denoted by the sign capital D with the subindex x and dilation factor 1 over k. So the horizontal dilation by the factor 1 over k operates in such a way that the point xy changes its first coordinate to 1 over kx and y. So let's see this on parabola as before. That's our original x squared. If we want to graph 1/2 x squared, 1/2 is by the x, not outside of the function, but just by the x. Then, well, let's check some points to make sure that we confirm what's going on with points. So if x is 0, well, the g of x is also 0. If x is 1, well, the g of x is 1/4. X will have to be 2 in order to make it actually 1. Well, so 0, 0 is the same. At 1 is barely 1/4. At 2, instead of 4, now I have barely 1. So it's a lot wider function, similarly to the left, because we know the shape is symmetrical. We also know it's a parabola, it's not a straight line, so we need to connect those points with some curve. Maybe let's choose another point, for example 4. If x is 4, this becomes 2 squared, so it's 4. I need to go 4 across in order to reach 4 up. Similarly to the other side. So the parabola goes somehow like this. This will be 1/2 x squared. As you see, we multiply x by a small number 1/2, but the x-axis is actually stretched. Whatever the value was for 1, now the same value is for x equals 2. Similarly, we've got the value 4 for 2, now it's stretched and the same value can be obtained for x equals 4. So yes, it is stretched horizontally by the reciprocal number of the coefficient by the x. Well, now let's put combination of all the transformations that we talk about. Using the given graph of function f, as on the diagram, graph new function. So in order to do that, maybe it's a good idea to list transformations first. We could dilate in x-axis, because x is multiplied by 3, by the factor 1/3 first, and then we multiply by 1/2 from outside of the function, so it's a dilation in y-axis, and we can say by the factor 1/2, and then use symmetry in x-axis, Or we can say at once by the factor of -1/2. That means every y coordinate will be multiplied by -1/2, and then we don't have to worry about symmetry. Okay, let's apply the first dilation. Let's use blue color for that part. So every single x coordinate will be multiplied by 1/3. So for example, this point, which had coordinates 3 and 3, x coordinate of this point will be 1/3 times 3, so it's 1, but 3 is still there. The y coordinate is unchanged. Similarly, this point will be closer. It becomes -1/3. Therefore, our shape will look somehow like this, since 0, 0 is at the same place. So we have the new shape like this. And the last one may be in purple. So now we apply dilation in y-axis by -1/2. Therefore, the point that had y coordinate equal 2, it will become -1, because 2 times -1/2 is -1. 0, 0 obviously stays at the same place, but 3 times -1/2 is -1.5. So the graph will look like this. And this part. And that's a constant piece. So the overall graph is the purple one. This is the graph of g of x. Okay, let's do the same for function h. If we start with f of x, then the next closer function will be f of x plus 1. And to reach this graph, we apply translation by the vector -1, 0. So one step to the left. Then we can multiply by 2. So the next step will be 2 times f of x plus 1, which can be obtained by applying dilation. You multiplying the y value, so in y-axis, by the factor 2. And to be closer to h, your final h of x is the same as the previous function, -3. Which can be obtained by applying translation by the vector 0, -3. So, starting with the red one, let's do the translation first in yellow. -1, so all important points go to the left by 1. So the graph will look somehow like this. Okay. Now the next step, let's draw in blue. So it will be dilation in y-axis by the factor 2. So instead of value 2, we'll have value 4. Instead of value 0, we still have value 0. Instead of 2, we have 4 again. So it's stretched vertically like this. And finally, maybe purple moved everything 3 steps down. So this vertex at -1, it goes to the level -3. This one goes here, that one goes there. And we draw the final shape by connecting the important points. So the purple one is our final shape of h of x. In the next exercise, we have given some information about function f. We know that f of -1 is 3, f of 2 is -3, and we need to give the coordinates of 2 points on the graph of the new function created out of f in the following way. So what we really need to do, we need to observe the pathway of those 2 points. What will these 2 points do when we perform appropriate transformations? Well, let's list those 2 points. First, -1, 3, and 2, -3. So, the first step, what do we do with the function? Well, let's subtract 1 from inside, which means we apply translation by the vector 1, 0. So, one step to the right. That means that we need to add 1 to each x coordinate and leave the y coordinate the same. So our points become 0, 3, and add 1 here, it's 3, -3. The next transformation will be multiplying the function by 2, which means we're going to dilate in y-axis by the factor of 2. That causes that y-coordinate of each point will be multiplied by 2. So our points become 0, 6, and 3, negative 6. Finally, we use the translation by the vector 0, 3, which adds 3 to each y-coordinate, and we obtain the final points 0, 9, and 3, negative 3. These 2 points belong to the g function. In the next example, we have given such information about f. We know the domain and we know the range. Find a sequence of transformations of the graph of f to obtain the graph of this particular function and state the domain and range of g function. So first let's try to rate the transformations. Let's focus on what we have inside the function. We have 2x plus 6. In order to obtain this 2x plus 6, it's a good idea to pull the 2 out and see how x will actually have to be changed to create whatever's inside the f. So we have a situation 2 times something, and this something is obtained by adding 3 to the x. So the first transformation that I will propose, starting from f of x to create f of 2x, is dilation in x-axis by the factor of 1/2. Then this is a new function of just x, so we're going to move only x to create f of 2x plus 3. That will be done by translation by the vector negative 3, 0. And the next step, multiply the function by negative 1/2, so we are very close to what we need. You can already multiply this inside. This will be caused by dilation in y-axis by negative 1/2. And the final stage, which is our g of x, negative 1/2 f of 2x plus 6 plus 1, is obtained by translation by the vector 0, 1. So those are the transformations that we need to apply to the domain and range. When we observe the change in domain, we really observe the first coordinate, and the change in r will be observed by change in y coordinates. So starting with the original domain of f, which was negative 4, 1. Let's go through the transformations. Dilation in x-coordinate changes the x-coordinate of the points, and it changes it by multiplying by 1/2. So each coordinate of these outside points of the interval will be multiplied by 1/2. So our domain will change into negative 2 and 1/2 just after the first dilation. Let's record this. That's the effect of dilation in x-axis by 1/2. Next, the translation by the vector negative 3, 0 causes that every x-coordinate of the domain will be moved 3 steps down. So you really subtract 3 from the x-coordinates, so it will be negative 5. And 1/2 minus 3 is negative 2.5, or rather 5/2. So that will be the new domain, because of the translation by the vector negative 3, 0. The following transformation refers to y, and the last one also refers to y. So this is actually the final domain of our g function. So that's what we've been looking for. Let's do the same with the range. So range of f function, it was given as negative 2, 6. And the first transformation that actually applies to range is not this one, not that one, but dilation in y by negative 1/2. Dilation in y by negative 1/2. That means that I'm multiplying the y coordinates by negative 1/2, that becomes positive 1, and -3. The next transformation will be adding 1 to the y coordinates. So this becomes 2 and -2. And that's the range of g function. Here we've been translating by the vector 0, 1. We cover nearly all important transformations except for absolute value. How absolute value affects the graph of the original function. If the absolute value is done outside of the function, then all the negative values of f will become actually positive, and positive values do not change. So what's happened is we reflect the negative part of the graph in x-axis and leave the positive part of the graph unchanged. We can picture it out on the parabola x squared minus 4, which looks like that. We start with -4, go 1 across 1 up, 2 across 4 up. The basic parabola moved down by 4. So this yellow graph is the graph of x squared minus 4. And we want to create a graph of absolute value of x squared minus 4. This graph leaves the positive part of the yellow graph exactly the same, no change. However, the negative graph will be reflected over the x-axis. So -4 will become 4, and the shape will look like this. So the red shape is the shape of absolute value of x squared minus 4. A little bit harder to understand is obtaining a graph of a function f of absolute value of x inside the function, just around the x. So what we do to obtain this graph? Well, let's maybe look at the example first. We'll start with graphing x minus 1 squared, which is f of x. X minus 1 means that the basic graph goes one step to the right, and it's 1 across 1 up, 2 across 4 up. So that's the basic parabola, moved to the right by 1. That's 1, and that's 1. And now if I want to analyze what this f of absolute value of x really means, is if x is positive, then this really means the same as f of x. So for the positive part of the graph, I should keep exactly the same shape. There is no change here. It's the same function. However, if x is negative, then we really have f of negative x, because after dropping absolute value, x becomes negative x for negative x's. So we know how to graph f of negative x from the original yellow graph. Well, we're supposed to use symmetry in y-axis, so normally the graph will look somehow like this. However, we can graph this only in the negative part, which means that we are reflecting the graph to the right of y-axis over the y-axis to the left. So it becomes like that, blue V. However, this part, this yellow part of the graph, it is totally forgotten. It's not there at all. So we erase the left part of the graph, erase totally, and redraw the right part of the graph in reflection with respect to y-axis. So keep the right part of the graph and flip it to the other side. However, the left one is forgotten. So this final blue graph is the graph of the function absolute value of x minus 1 and then square it. You can check on that. For example, if I plug it in point -2, for the x I have absolute value -2 minus 1, square it, which is the same as 2 minus 1 is 1 squared, so yes, it is 1. This indeed belongs to the graph. And the final exercise is to graph this funny function with two absolute values. So if we want to list the transformations, we'll start with the line just x minus 1, which we know very well how to graph. Then we'll apply absolute value to it. Then we subtract 1 outside of the function, which means we use translation by the vector 0, -1. And finally, we apply absolute value to the previous function to get f of x. So let's start with the original function in yellow. That's just a line starting with -1, and it's a diagonal like this. When we apply absolute value to it, we reflect the negative portion of the graph up. So the red one is the graph of this formula. Now the next stage, let it be green. That means drop the red one step down. So this vertex becomes here and diagonally like this. Drop it down. Finally, the purple one, whatever we had before, that means green graph, apply absolute value to it. So if you see something that is below x-axis, flip it over to make it positive. Flip it over x-axis. And the rest has to be redrawn. So the purple graph is the final graph of this function. It's like a funny W shape. So the purple one is our function f of x. And now, since we already know all the transformations, on the last slide I present to you the summary of transformations. So for example, if we add a constant outside of the function, we move the function up or down vertically by the vector 0a, the same number as we added. If we add or subtract a constant inside the function just by the x, then we move horizontally in opposite direction that the sign would indicate. If it's minus, go to the right. If it's plus, go to the left. If you have a minus outside of the function, we reflect the graph over the x-axis. If you have a minus inside by the x, we reflect the graph over the y-axis. If we multiply function by a constant, it is a vertical stretch by the same constant. If we multiply just the x by a constant inside the function, then we have a horizontal stretch by the reciprocal of this constant.